Assalamualaikum warahmatullahi wabarakatuh, and very good day. This is a lecture on pressure measurement part 2. So in the part 2, we're going to see about the pressure transducer. If you look at the notes, we will talk about pressure transducer, which is the elastic element that one of the important components in the pressure transducer, which is we have three types of elastic element, which is the Bourdon tube, bellows and capsule, and diaphragms. And after that, we're going to see the calibration method of the pressure transducer, which is to use the dead weight tester. So pressure transducer is actually a function to convert pressure into a mechanical signal or electrical signal. So for this case, we have two kind of sensors, which is primary sensor and secondary sensor. What is primary sensor and secondary sensor? In details, you better visit the earlier topic for this subject under the fundamental of measurement and instrumentation. So for the primary sensor in pressure transducer, it uses the elastic element, which is this is the part where it is the first contact between the sensor, the transducer, and the physical signal that we want to measure, which is the measurand. For this case, the elastic element will deform, or we bend, or will expand due to the existence of pressure, or the pressure is increased or decreased. The common elastic element for the pressure transducer, which is as mentioned earlier, is a Bourdon tube, bellows and capsule. They are the same construction, the same shape, but it's the same concept, but have a different concept. And the last one is diaphragm. And then for the secondary element or secondary sensor element, it is where it's convert the mechanical motion or deformation from the elastic element into the electrical signal, right? Not only it can convert into electrical signal, it also, if the sensor is not connected to the electrical device, so as a secondary element, we also can use the mechanical indicator, for example, a needle, or maybe just mechanical indicator. Okay, we'll have a look after this slide. So the most important is we need to look the block diagram so that we can understand the whole structure of pressure transducer, any kind of pressure transducer. So pressure comes in and it interacts with the elastic element, and elastic element will produce a motion or deformation, and then that deformation or that motion will be converted by using some sort of electrical or any mechanical elements or electrical elements that can convert that motion into electrical signal. But we actually like to focus on the electrical signal, because nowadays we are looking for more sensors with this, which is a digital output. So it can be connected straight away to the computer for any kind of monitoring or any kind of measurement. So like I said, if you look at the slide, it's mentioned that the output voltage can be recorded, okay, and then it can be viewed, it can be shown, display with the oscilloscope or any kind of suitable display that we want to use. So this is actually the type of uh, uh, the one of the example of the sensing element, the first primary sensor, I mean, which is we have a diaphragm, bellows, capsule, uh, tube, which is a tube. We have a straight tube, Bourdon tube, C shape, twisted Bourdon tube, helical Bourdon tube, spiral Bourdon tube. This is actually example. This is actually example of primary sensing element that we can use for the pressure transducer. So we're going to look one by one. So the Bourdon tube, this is actually one of the sensors that I actually already discussed in the earlier topic for the pressure for the measurement and instrumentation, the fundamental of measurement itself. We have a look on this one. So the concept of Bourdon tube is it have a curved metal tube, and then the cross section is elliptic. So that curved metal tube will deform if there is a pressure inside the tube. Okay, it will deform, and that deformation can be related to the amount of pressure uh, that 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 um, that insert or going into the metal tube. So the if you look at the Bourdon tube concept here, this is actually one of the commercial pressure gauge. The inside the commercial pressure gauge, we have a Bourdon tube as the main mechanism. If you look at the cross section of the tube here, sorry, look at the cross section here. Yeah, so it's like elliptic shape. Okay, so when a pressure go inside the tube, it will deform the whole structure, the C shape structure here, and then it will the deformation, that motion will link to the this mechanical linkage, and the whole thing will deform here, and then the spring, the pinion, the needle will move to indicate the level of pressure inside the tube. So it can be used for about 10,000 into a few hundred thousand, thousand of Pascal, thousand. We're talking about thousand. So it have several range for this one, but usually if you buy a cheap one, it can be up to 6 bar. Okay, 6 bar, which is 6 bar is equal to 6 ATM or 600 kilopascal, something like that. Roughly something like that. All right. Then we have the next is the bellow. It's actually a thin wall, flexible metal tube. It formed into deep convolutions and sealed at one end. So one end has no end, no opening, and the other end is we have opening to make sure that the pressure comes in, and that pressure will move automatically. Will give a motion to the metal tube in only one direction. Okay, one direction, and of course that motion can be used to indicate the pressure. So the more pressure will give more motion. Same concept with the capsule, but the difference is the shape. The shape of the flexible metal tube. Okay. So all bellows and capsule can be connected together with the potentiometer, pressure transducer, which is some sort of like the variable resistor. It use a variable resistor where that motion of these the arm here will give the variations in terms of voltage output. So it's related linearly with the motion of the it's actually straightforward. The motion of the bellows or capsule will give the variations to the electrical signal in this potentiometer pressure transducer. We also can use another one concept, which is LVDT, linear variable displacement transducer. For the potentiometer, we look at the we look at the variation of electrical signal by the potentiometer. But if you use the LVDT, it will convert the displacement of the bellows or capsule also into an electrical signal, but they use a concept of metal and core. So, magnetic and core. Magnetic and core. When we look on this structure of LVDT later on, when we look into topic of accelerometer or displacement sensor. Alright, so the other example of elastic element for the accelerometer, for the pressure transducer is a diaphragm. Diaphragm is actually consists of a membrane. Membrane can be a flat, can be rectangle, can be any shape. Okay, it can be a flat membrane. Okay, or it can be a corrugated shape of the diaphragm. So the membrane can be used a metal structure, also can be used on metal. So the effect is actually the range. If you use metal as the membranes, it can have a large range for pressure measurement, but less sensitive if you use if you use another type of non-metallic material, which is, for example, rubber. Rubber can have a very sensitive measurement, but the range a lot lower, lot lower than if you use a metal membrane. The different type of pressure transducer can be used either for the differential pressure or absolute pressure measurement. So this is actually one of the example where the diaphragm is in corrugated diaphragm. So it contains of a number of corrugations. So its function is to it functions to increase the diaphragm stiffness and also to increase the effective surface area. So it might be more sensitive and it might be more better in terms of giving large amount of motion due to the pressure. But in terms of accuracy, it's still to be studied lah, the accuracy. Sometimes the corrugated can be more accurate than pressure transducer. For the membrane type of diaphragm. But sometimes a membrane also can be more accurate. But depend on the application or depend on the design of the diaphragm itself. Okay. So among of these three type of sensing element, the diaphragm is actually more interesting because it can be used for dynamic measurement. Okay. But it have to be careful design. Otherwise, it cannot function properly. First thing you have to see is actually the how much the deflection can be occurred on the diaphragm due to the pressure, and also we have to look into the dynamic consideration. How fast? Because I said diaphragm can be used for dynamic measurement, we need to see how fast that diaphragm can capture the dynamic signals of the pressure. For the deflection, by default, usually we can say it must be designed so that 1/3 of the thickness thickness for the diaphragm. Okay, this is we talk about the membrane type of diaphragm. So the thickness is T, the deflection is Y. So if you look at in the equation here, the relation between the thickness, all the properties for the membrane can be related to the deflection, maximum deflection of the membrane itself when we have pressure. So we can use this equation to design the structure when actually we look at how much the pressure that we want to use, okay, for this pressure transducer, and then from that information we can design the shape, or we have the shape and we want to we have the shape or we have the dimension of the pressure transducer, and we want to see how much this pressure transducer can sense, okay, can acquire the pressure signal. So E is the bulk modulus in unit of Newton meter square, and then we have R for radius in meter, thickness also in meter, and the Poisson ratio for the diaphragm material. For the dynamic consideration, we want to see, like I said, we need to see how much the vibrations that can how much the frequency maximum that can be uh, sensed, can be acquired by this sensor. We're actually looking at the omega n, which is the natural frequency of the diaphragm. We need to avoid to the dynamic pressure to match with the natural frequency. Otherwise, it will it will damage the diaphragm, or it can give a large error to the measurement. So the same information, ET as a thickness, E is a stiffness, G is the gravity, or in this equation we usually use G as 1 kilogram per meter over N as 2. Okay, N as power of 2, and we have V as a Poisson ratio, and this is actually rho for the density. All right, so if we look at the example here, so let's say we have steel 5 centimeters diameter as the diaphragm, which is actually metallic diaphragm, which is we have steel as the membrane type of diaphragm, which is E 200 gigapascal or not Newton or meter square. The Poisson ratio is 0.3, and the density is about 7,800 kilogram over meter cube. And then we need to use this pressure transducer for about 1.4 megapascal pressure, so that we need to calculate how much the thickness, so that it can get the maximum. It can get the maximum deflection for the pressure for the diaphragm. So we know that in the previous slide we see that actually the deflection must be less than 1/3 of the thickness. Okay, and then we can use the given equation, y max equal to 3p1 of 1 minus Poisson ratio, this one. Okay, for the if we want to calculate thickness. So look at here, y max is actually can be convert, because it can be changed to 1/3 t, like in the previous slide. This one, y must be less than 1/3 of the thickness. So we convert this equation here. So from that we can rearrange. Okay, let t as the main unknown here to be calculated, and you can find the answer for the thickness. all the value inside the equation is given inside inside the question here. So the same here, just plug in all the numbers and then you can easily calculate the natural frequency. So we need to avoid natural frequency. So whatever the frequency or the pressure comes in, we need to make sure that it's lower than this value. So by the calculation, we can say, sorry. So we try to calculate this one, and then we discuss the answer. All right. So I leave it you to do the quiz 2, but with your own time. So now we look at the secondary element that can be used, can be connected to the diaphragm as the previous one, which is the bellows and capsule. It can be used a potentiometer or LVDT as a secondary element. For the Bourdon tube, earlier we used the mechanical indicator as a secondary element. For diaphragm, we have 3 types of secondary element, which is a strain gauge element, capacitance element, and piezoelectric crystal element. Okay, so we look one by one. So the first is a strain gauge. So if you look at the structure inside the notes, so we have a diaphragm here, any kind of diaphragm, metallic, non-metallic, rubber or whatever. So to measure the deflection, the motion or the deformation of the diaphragm, we put the strain gauge strain gauge. We know that strain gauge we have 4 legs. Either we use all the 4 legs or only 1 leg or 2 legs. It's up to you, up to your design. So that we just put the strain gauge and then we connect cable. We make sure we secure the cables, and the output can be connected to the display to measure the signal, the electrical output. But you must remember that the strain gauge need to have electrical voltage in as well. Otherwise, it cannot function. So if you look at another one, I don't want to discuss on how the strain gauge can be used to measure the strain, because we already looked into that in the previous lecture. But for this one, a capacitance type of secondary element, which is it used the gap, the capacitor gap C value. So if you look at the equation here, very straightforward. C equal to C small c here indicates the proportionality constant, and then this is strain. A is the what I call the area, effective area, and T is the thickness. Sorry, the distance. The distance from diaphragm to the capacitor, the plate capacitor, metal plate of the capacitor. We can say thickness or we can say gap between. Okay, so from this equation, just plug in all the equation. We have then we can find the C. Sorry, that C here is linearly related with the strain here. So the more strain, you can increase the value of C here, the capacitance. Okay. Let's say we have a constant, constant. That strain also related with the gap the gap. Okay. So the more gap, the more strain, the more gap But sorry, for this case, the gap is constant we let it constant. At the earlier stage is constant, and when there is pressure comes in, it will deform and give us strain. Okay, regardless of whatever gap during the measurement, it gives the strain. This is actually T is the gap, the initial gap. So then the strain here can be related to the C is capacitance here, and you can plug into the equation here, and you can find the value for the variation of the electrical signal. C1 is actually the I think it's have a value for C1 here. We will look we will look in the next slide. Sorry, the C1 is actually is here. It's actually given. It's fixed value. Fixed value. E1 E input also fixed value. It's a fixed value. U actually suggests the value for C1. So if you look at this equation, if we have a large value for C1, okay, large value for C1, it also can increase. It can, sorry, if you look at here, if the C is increased, okay, due to the increase of the strain, what happened is the E is reduced. E is reduced. E value is reduced. Okay, so if you change the value either C1 or E1, E is the voltage input. Either you change it both value, it can reflect to the sensitivity of the whole measurement. Okay, for example, if you increase the C value here, whatever value happen here, it will sorry, if you increase C1, so the C also affected lah. It will also amplified lah. I think it's also amplified. It's also amplified. Okay. So if you look at the example here, so C1 is given 0.01 plus minus 0.05 microfarad, and the input value is 5 voltage, and the plate have a overlap area, which is the T is 8. Sorry, the area A is 8 millimeter square, and the air gap, this is T. T is 1.5 millimeter. So by using all this information here, and then we know that the plate about the plate move about 0.2 millimeter. So we can easily calculate the capacitance and easily calculate the output voltage because it's just plug in the number. Okay, we have all the values, plug in the number, and you can easily calculate the E naught, E output. Okay. So considering that it's actually for this case, the plate move apart by 0.2 mm. So it will the T initial is actually the earlier T is actually the 1.5. Okay, 1.5 here. See 1.5. So the gap, sorry, if you look at the equation, the plate move apart by 0.2, which means the plate move closer 0.2 mm. So it will, sorry, it will increase. Sorry, it move apart. It increase 0.2 mm. Either increase or decrease. It will plus minus 0.2. For this case, it calculate for if increase. So it become 1.7 mm. So if the thickness, the gap is 1.7, just plug in the number. You can get the C here value here, C value here, and then you plug in the number, the equation here. This equation you can find is 1.2. So if you reduce the gap, which is by 0.2, it becomes here. It become 1.3 lah, 1.3. So you put here in the value here, then you can have increased value of voltage. Okay, that's the effect of the air gap lah. We didn't talk about strain yet. This is actually about the air gap. Yeah, air gap. So the piezoelectric pressure transducer, we use it utilize the piezoelectric materials as the medium to measure the motion of the diaphragm, the motion of the diaphragm. Okay, for example, if you look at the diaphragm here, for example, it have pressure from downwards here, moving to upwards. The diaphragm will press the piezoelectric materials here, somewhere here. Okay, so it will give the electrical output, and then straight away to the lead wire and connector, and also and straight away go to the display lah, to the electrical reader, any kind of electrical reader lah. Okay, so it's just straightforward. Okay, all right. So that one is actually for the diaphragm. So if I can recap for pressure transducer, first it use a primary element, which is we have a lot of primary elements, Bourdon tube, bellows and capsule, and also diaphragm. So each of these elastic element, we need to use a secondary element to show to display whatever because the first element is actually just a motion or just a deformation. It cannot give any indication or values. So this sensitive element, the secondary element, will convert that motion into a display or indicator. So Bourdon tube have different indicator, which is mostly mechanical, and then the bellows and capsule using potentiometer or LVDT, and the last one diaphragm using three types, which is strain gauge, piezoelectric elements, and also it can use capacitor types of element. Okay, so then we need to look at this another one, also pressure transducer, but it is close to us, which is the microphone. The concept of microphone is actually it convert the pressure, the sound pressure or acoustic pressure, which is the sound is also acoustic pressure. It convert that motion of acoustic pressure into electrical signal. So for example, if dynamic microphones, we have sound wave, then it will push the diaphragm. Okay, the diaphragm will move together with the coil here. The coil, it move the coil. The coil will move with magnet. Okay, so that it will give the electrical signal. This one is actually the old concept of microphone the telephone, the old concept of telephone. I use this concept. Sound wave hits the coil interact with the magnet, and they give electrical signal. Electrical signals can be related to the sound wave. And then in other parts, the electrical signal converted into sound also by using this mechanism, just opposite mechanism. Not only with using the magnet and coil, it also can use a capacitor type, which is a condenser. You know, condenser or capacitor type of circuit. It need to have a gap, diaphragm, a metal plate. So that gap will indicate, will give. I mean, if we monitor the gap, we can monitor the voltage. Okay, due to the sound wave touching the diaphragm. And then that the electrical signal relate to the signal of the sound. Okay, the same concept with the one that in diaphragm, because this microphone also a diaphragm, it's like a diaphragm. Okay, and we also can see the ribbon ribbon type of microphone. Okay, so that's actually the same concept with the diaphragm. And then we look at the last parts of the lecture here. Is the calibration of the pressure transducer. We're looking at the dead weight tester. Okay, if you look at the construction of the device, which is we have applied load. Okay, up to here, applied load. We give the load here, and then straight away, this is actually the area. We have area here, and we have a load, so we can calculate the pressure. The pressure, we know that if we transfer the pressure to the fluid, it will distributed uniformly all inside all the liquid pressure, liquid inside the inside this pipe. So all closed so that the pressure need to go somewhere. So the pressure will go somewhere open, for example here, and then this is where we put our pressure transducer. So we know that applied pressure here from this structure here, and then the pressure transducer that we put here should indicate the same value as the calibrated amount here, calibration amount here. That's how the calibration done. So we had a lot of example. We have different kind of shape, dimension of the dead weight tester. The difference in terms of accuracy, okay, repeatability, and so on. Okay, they use the same concept for all type of dead weight tester here. The only difference between them is actually the price. This can be 20,000 ringgit. It can be 5,000 ringgit. It depends on the accuracy that you're looking for the sensor. All right, so that one I will finish the lecture with this final slide. With that, I would like to say for the pressure transducer, the whole pressure transducer is very interesting because the pressure measurement can be used for two kind of measurement, which is the dynamic measurement and also for the static measurement. The temperature also the same. Okay, the strain measurement also the same. Need to look at the both static and dynamic measurement. Okay, so with that I close the topic for the pressure measurement. So see you on the next topic. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.